In this lecture, we are going to talk about some special type of topological spaces which are called compact spaces. In order to study compact space, we will be using covering and open covering of a topological space. Let me first define covering and open covering of a topological space, and then we will define compact space. Okay, now here is the definition of covering and also open covering of a topological space. Let's say X is a topological space. X is a topological space then a collection is script A of subsets of X is said to cover X or said to be a covering of X if the union of the elements of this collection script A is equal to X, and if each element of this collection script A is open subset of X, then this covering script A is called an open covering. It's called an open covering of X. Now from this definition you can see that covering of a topological space X is simply the collection of subset of X such that their union is X itself, and if each element of the covering is an open set of X, then that covering is called an open covering of X. Now let me give you a couple of examples of covering and also open covering of a topological space. Let's consider a topological space, or let's consider the set of real number R with the standard or order topology. That means the open set in R are open intervals. Then let's consider this collection of the subset of R. In fact, let's consider this collection of those intervals n plus 2, such that n is an integer. So we have taken the collection of those open interval, they are basically the open set in R in the standard topology, then this collection is an open covering of R. That means if we take the union of those open interval or open set, then that union is going to be in the entire real line, which we can see from this graph. Let's say this is the center, this is 1, 2, 3, and you keep going. This side is positive infinity, that's negative side of a real line. And now here our intervals are those. So it says the elements of our collections are those open interval n to n plus 2, where n is an integer. For example, if n is 0, then our interval or open set is going to be 0 to 2. You plug in 0 for n, so it's going to be 0 to 2. And if you plug in 1 for n, then our next interval is going to be 1, 2, 3. And then if you plug in, it's open, is not closed. And then if you plug in 2 for n, then it's going to be 2 to 4. Now you can see from here, so if you take the collection of all those intervals, then that collection is going to be then the union of that collection is going to be R itself. And similarly, you can take the negative side. For example, if n is -1, then it's going to be from -1 to 3, -1 to +1. So, and then you keep going. So, if we take their union, obviously that's going to be the real line itself. That's why this collection is an open, is a covering of R. And since we are taking the standard topology, in the standard topology, each open interval is open set. That's why it's also open covering. Let's consider another collection of open interval in R with the standard topology. Now this time, so our the elements of our collection are those interval n to n plus 1, and where n is an integer, so it's not a covering. It's not a covering. It's not a covering of R. You can see this one from here. Let's say we have this real line. This is positive infinity, that is negative infinity, and then we have center 0 here. This one is 1, and then let's call 2, 3, and this is negative side of real line. And now let's graph those in interval here. Let's say if n is 0, then it's gonna be 0 to this open interval 0 to 1, and then if n is 1, is 1 to 2, so 1 to 2. When we take the union of these two intervals, now you can see we are taking the union, our intervals are open, so that means 1 is missing from here, okay? And if you, let's say n is 2, then our next interval is gonna be 2 to 3, so 2 is missing. So when, if we take the collection of those open interval here, all the integers are missing. That means their union cannot be R itself, so it's not the open covering of R. In fact, it's not the covering of R. Even the intervals are open, but their union is not is not R. That's why it's not a covering of R. So these are the example of open covering. First one is an example of open covering of R, but the second collection is not a covering of R. Okay, next I'm going to give you definition of compact set or compact topological space, and then we'll give some example. Okay, so here is the definition of compact topological space. A topological space, space topological space X is said to be compact. It's said to be compact if every open covering of X contains a finite subcollection that also covers X. Now you can see from the definition, a topological space X is said to be compact if every, so here is the word every, is very important. Every open covering of X has a finite subcollection which also covers X. That means every open covering of X, we can pick finite number of elements from every open covering of X, and that those if we take the union of those finite number of elements of our open covering, that union should be X, and then X is called compact, otherwise not. And it says that every open covering, no matter which open covering you choose for your topological space, that open covering should have finite number of elements, and if we take their union, the union should be X. Okay, this is the formal definition of compact space. Now let me give you few example of compact space and also some which are not compact. Let's say this is the example number 2. If you have any finite set, then that or if you have any finite topological space, that topological space is compact. So any finite space X, finite space means it has finite number of elements. Let's say x1, x2 up to xn. These are the element of our finite space X. So any finite space X is compact. So by definition, if this space is compact, no matter which open covering of this space we take, that open covering should have finite number of element, and if we take their union, the union should be X. And it is easy to show. It is easy to show this definition is true for the finite set. Okay, so here is a quick proof for let's say if script A, whose element, let me denote those elements by AI, is an open covering of X. So this is the collection of AI, which is the open covering of X. That means if each AI is open, and if we take their union, then it's gonna be X. Now we are saying X is compact, so that means this open covering, it should have finite number of AIs. If we take their union, the union should be X. Is an open covering of X. Then since this is open covering, that means each element of X, those x1, x2, xn, they have to be, each element of X, they have to be in at least one of the AI, because the union of AI is X itself. So is an open covering of X, then each element or each element in X belongs to one of the elements of script A. Let's say x1 is in A1, x2 is in A2, and then let's call xn is in an, because x has only finite number of elements, x1 up to xn, so x1 is in A1, x2 is in A2, and xn is in an. Then we can say that since x1 is in A1, x2 is in A2, and xn is in an, so if we take the union of those A1 up to an, that is x is obviously going to be the subset of those union of that union. Okay, so we found that finite collection of the elements in script A, their union is going to be x itself. That's why this x is it's compact. So here we just saw that if you have a finite topological space, then it's always compact. Okay. Another example: any space, any set, or you can say set, any space with indiscrete topology is compact. And this is obvious if you consider a space with indiscrete topology. In that indiscrete topology, there are only two open set, empty set and the set itself. So let's say if the topological space has an open covering, then since the open covering has only two elements, empty set and the whole set X, so so obviously that one is compact, because there are only two open sets in discrete topology. So any space, no matter it is finite, infinite, if you consider in discrete topology, then that space is compact. Now I'm gonna give you a couple of examples of spaces which are not compact. Any infinite set with discrete topology is not compact. Remember, in the discrete topology, those one point sets are open, because discrete topology of a topological space, it's just a power set. In power set, those one point sets are also in the power set. So if you are considering a topological space with a discrete topology, then those one point sets are open. And if a set is compact, or if a topological space is compact, every open covering should have a finite subcover of that topological space. Since our space is infinite set or is infinite space, so there are like infinitely many those one point set, and if we take the union of those one point sets, then the union is going to be the set X itself, so that the collection of the one point set is gonna be open covering. But since our set is infinite and the collection has infinite number of one point set, so if we take those only the finite number of one point set, then their union is not going to be same as X, because X is infinite. But if we take only the finite number of one point set, then obviously the union of those finite number of set from our open covering is not going to be same as X. That's why in any infinite set with discrete topology is not compact. Here is the more popular example of a space which is not compact, that is real line with the standard topology. Consider R with the standard or order topology. Order topology then R is not compact. So we are considering this standard topology. Okay, the topology, which topology you're taking, that is very crucial here. Okay, so here we are saying R is not compact. That means if we find an open covering which doesn't have finite subcover, then that's enough to say R is not compact. And we have already seen that this collection of those open set or open interval because let me add this here, because this collection, because the collection is open covering, this collection is the open covering but does not have a finite subcover, okay, which we can see here. So we have already seen that this collection of those open interval is an open covering of R with standard topology, but this collection doesn't have the finite subcover, or we cannot pick finite number of intervals here, and if you take their union, it cannot be R, which we can see from here. Let's say this is the real line. So our covering is, if this is 0, then it's 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. So our covering looks like this one, 0 to 2, and then I'm using those different color to differentiate the covering. Okay, now this is one of the element of our open cover, and this is the another one, and then this is the other one. Since there are infinitely many such open interval, that's so that when we take their union, it's gonna be R. But if we take only the finite number of those open interval, like if we just take those 3 here, then obviously those 3, they cannot, their union cannot be R here. So we cannot take infinitely many. We have to have finitely many. So obviously those finitely many, if we take just the finitely many open interval, their union cannot be R. So that R is not compact. We have this open covering which doesn't have the finite subcover. That's why R is not compact. Next example number 6. The interval, this half open interval 0 to 1, 0 is not included but 1 is included, is not compact. If it is not compact, then like in our previous example, you should be able to find an open covering which doesn't have the finite subcover. Now for that one, so let me use this graph here. So we have this, we are taking the interval 0 to 1, and this is 1. So 0 is not included but 1 is included. So we are saying this half open interval is not compact. So like I said, if it is not compact, we should be able to find a finite subcover. Sorry, we should be able to find an open covering which doesn't have a sub covering, finite sub covering. Okay, so Now let's take this collection. It's not compact since the open covering let me call that open covering. It is script A, and the elements of these open coverings are those open intervals. Okay, 1 over n to 1, and n is positive integer. So this interval is open because we are considering a subspace topology. Okay, subspace topology. In subspace topology, a set is going to be open if you take the intersection of this. If you take the intersection of this interval with an open set in R, then the result is going to be open in subspace topology. So those type of interval, they are going to be open in subspace topology in this interval, because if we take the intersection of this interval with one of the open interval in R, then you're gonna get this type of the interval. That's why this collection is each element in this collection is open, and also we are saying is open covering. So now let's see whether the collection of those interval is it's going to be a covering or not. We have already seen each elements, they are open in subspace topology. Now let's see whether this collection is covering of X or not. So now you can see our first sub interval, or our first element in this interval, in this collection, is going to be if you plug in 1 for we are only taking the positive integer. So if you plug in 1 for n, that's gonna be 1 over 1 1. So it's basically it's kind of just the point 1 itself. Okay, is 1 open interval 1, close interval 1, so it's just like the 1 point set. And if you plug in 2 for n, so it's 1/2 to 1. So it's, let's say this is 1/2, and this one is the one, this is the our second interval. And if you plug in 3 for n, so it's gonna be 1/3. So this is 1/3 to 1. And if you plug in 1/4 for n, then that's gonna be 1/4 open interval. So now n is any positive integer. So when you take the bigger positive integer, you're going to closer and closer to 0. And if you pick very big positive integer, then it's gonna be very close to 0, and 0 is not included. So when you take n is very big positive number, positive integer, then you are close to 0. Since we don't have to cover 0, that's why when we take their union, the union is going to be this interval, this half open interval. That's why this collection is a covering. And then like I said earlier, each interval is open, so it's a open covering. Okay, if it is if this interval, this half open interval, is not compact, then this open covering should not have a finite number of elements such that their union is this interval 0 to 1, or half open interval 0 to 1. And that one is obvious, because let's say if we pick a first two element of this collection, then that's gonna be just the singleton set 1 and this interval 1 to 1. So, and then you can see easily, if we take their union, the union of first two element of this collection, then we cannot say that union is from 0 to 1. And if you add one more, then just you going to from 1 to 1/3 to 1, then it's obviously not equal to 0 to 1. And if you add one more, then the union is going to be 1/4 to 1. But by picking those finite number of element of this collection, and if you take their union, that cannot be the whole interval, whole half open interval 0 to 1. In order to be the union, this interval from 0 to 1, we need to take infinitely many. We have to take this n is a very large positive integer. That's why this collection cannot have a finite number of elements such that their union is this interval, so that this interval is not compact. Okay, just let me write down this thing. Since this open covering contains no finite subcollection, covering this half open interval 0 to 1. That's why this interval is not compact. Not only this half open interval, even if you take the open interval 0 to 1, that's not going to be compact. You can use the similar argument. And also the open interval 0 to 1 is not compact by a similar argument. You can use the similar argument to show this open interval 0, 1 is not compact. So here what we have seen is our half open interval is not compact, open interval is not compact, but the closed interval is going to be compact. That means on the other hand, this closed interval 0 to 1 is compact in subspace topology, which we will prove in upcoming lecture. Okay, so in our upcoming lecture, maybe not the next one, in the next one, so we will prove that those closed intervals in R, they are going to be compact, but not the half open, not the open intervals. Okay, all right, so this is another example of a space which is not compact, and this is kind of very famous example of a space which is not compact. Now let me give you one more example of a space which is compact. Okay, let's say this is example number 7. Again, we are consider R with standard topology or with the order topology. Then the subspace, this subspace, let's take our subspace as a union of the singleton set 0 and then the set of all reciprocal of positive integer. Okay, so this is the we are taking the subspace of R, which is the union of the singleton set 0 and then the set of those reciprocal of positive integer, and this subspace is compact. Okay, so basically what we have done here is, you can see in this graph here, we have 0 here, this is positive infinity side, this one is negative infinity side. So our x is this this point 0, which is the singleton set, and we are just taking the reciprocal of 1. So if you are reciprocal of positive integer. So if you are taking the reciprocal of positive integer, everything is going to be between 0 and 1. Okay, for example, if you take the reciprocal of 1, that's gonna be this guy itself. Okay, and then if you take the reciprocal of 2, so that's gonna be 1/2, and the reciprocal of 3, that going to be 1/3. It's going to be 1/3. And then when you take bigger and bigger number, so those the elements of our subspace, they are going to be more closer and closer of 0. And then we are saying that this subspace is compact. So if it is compact, then every open covering of this subspace should have a finite subcover, or should have finite number of elements whose union is X itself. Okay, for that one, so we have already seen that if we take this set, it's a subspace of R, then 0 is a limit point, okay? So which we have already seen that one. Okay, now like I said earlier, to show this space is a compact, every open covering of this space should have a finite subcover. So to show this one, let's consider an open covering. So let's consider an open covering script A of X. So we are just taking the open covering of X as a script A. Okay, so if it is open covering, then 0 is going to be an element in this 0 is going to be an element in one of the set in this open covering. Okay, let's call that element is U, because 0 it has to be in one of the element in this open covering. For an open covering script A of X, there is an element U of script A containing 0. Now you can see here U is open because this script A is open covering and U is an element of script A, and we are saying 0 contains in U. That means U is a neighborhood of 0. And as I said before, 0 is we have seen this before. 0 is a limit point of this set of this space X. So if 0 is a limit point and U is a neighborhood of 0, then this U should contains all but finitely many points of this set X. So here this U, since 0 is a limit point, then and U is a neighborhood of 0, so U should contains all but finitely many elements of this space X. Okay, just let me write down these things here. Then the set U contains all but finitely many points, contains all but finitely many points of the of our subspace X. Or instead of writing the element of X, just let me write down the set U contains all but finitely many points 1 over n. Now you can see here most of the point of X, they are already in U, but there are some finite number of points which are not in U. Okay, now what we're going to do here, we're going to pick the element of this open covering or the set from open covering for those elements of X which are not in U. And obviously there are only finite number of elements of X which are not in U. So like I said, we're going to pick the set from this open covering A for those elements of X which are not in U. Now choose for each point of X not contain in U an element of script A containing 8. Okay, so since U contains all but finitely many points 1 over n, now choose for each point of X not contained in U an element of a script A containing that element. Okay, then the collection consisting of those elements of script A along with U is a finite subcollection of script A that covers X. Okay, since all but finitely many elements of X they are in U, so there are only the finitely many elements are left out from X. For each of those elements we are picking the elements from the open covering containing them. So once we have the collection of those elements of the open covering and then add U, so that collection is going to have only the finite number of elements, and if you take the union of them, that's gonna be X. So this is how you can find a finite subcollection of any open covering of the given subspace. That's why this subspace is compact. So that's the another kind of popular example of compact space. So here we define compact space, and then we give some of the example of compact space and some of the spaces which are not compact. Now the next thing we're going to talk about the covering of subspace and also the compact subspace. Okay, so here is the definition. Here is the definition of compact subspace, and also the definition for the cover of a subspace. Let's say X is a topological space. Let's say X is a topological space and Y is a subspace. Y is a subspace of this topological space. Okay. X is a topological space if Y is a subspace of X, then a collection script A of subset of X is said to cover Y if the union of its elements contains Y. So here, to define a cover for the subspace Y of topological space X, we are using the subset of this topological space X. Okay, so we are defining a cover for the subspace in terms of the subset of X. Now I'm going to give a lemma here without proof. This lemma will describe the compact subspace in terms of the open set of our topological space X. Again, I'm not going to give a proof, but if you are interested in proof, you can take a look in Munker's book. So here is the statement. Let Y be a subspace. Let Y be a subspace of a topological space X. Then here X is a topological space. Then Y is compact then Y is compact if and only if, so this is if and only if condition, if and only if every covering of Y by sets open in X contains a finite subcollection that covers covering Y. So this is if and only if statement. So this lemma it describes compact subspace in terms of the open set of the topological space X. If Y is a subspace of this topological space X, then Y is compact if every open covering of Y by the sets in open in X, not by the sets open in Y. We are not talking about the subspace topology. So this Y is compact if every open covering of Y by the sets open in X that has the finite subcover for Y, then Y is compact. Okay. If Y is compact, then that's true. And also the converse statement is true. If every open cover of Y by the sets open in X contains a finite subcovering of Y, then Y is compact. So this is like if and only if statement, and this lemma it describes compact subspace in terms of the this open set in the topological space X, not in terms of the open set in Y. Okay, so in this lecture we define compact space. We gave many examples of the compact spaces and some example of spaces which are not compact, and also we describe compact subspace in terms of open set in the topological space. In our next lecture, we will study some important properties of compact space.